Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today's problem is problem number 3.32 out of Elementary Principles of Chemical Processes, 3rd edition. The problem statement says, perform the following pressure conversions, assuming when necessary that atmospheric pressure is 1 atmosphere. Unless otherwise stated, the given pressures are absolute. Okay, so we're just doing a bunch of pressure conversions, but there is going to be a little bit of talking about pressure heads and things like that. So converting between units like millimeters of mercury, inches of water, and then on the last one, centimeters of carbon tetrachloride. Okay, so let's start off with part A. So part A is very simple conversion that we're used to. They tell us how many millimeters of mercury there are, and we just use the conversions in the front of our book to divide by the number of millimeters of mercury in an atmosphere and multiply by how many psi are in an atmosphere, and those cancel out because they're equal to the same thing, and you end up changing units. Okay, so for part B, we've got similar kind of thing. We have feet of water, and we're turning it into kilopascals. So start off with this much water. We divide by how much water is in 1 atmosphere, multiply by how many kilopascals are in 1 atmosphere, and you get units changed. Okay. Part C says 3 atmospheres to Newton centimeters squared. Okay, so Newton centimeter squared is not a real unit that we use very often. I mean, it's a real unit, but it's not one that you use very often. Usually you use pascals or some form of pascal. But pascal is equal to newtons per meter squared, so you just have to turn it into pascals and then change the meter squared into centimeter squared. So 3 atmospheres, turn it into pascals, which is newtons per meter squared, and then you just convert the meter squared into centimeter squared. All right, that's it for part C, so let's move on to part D. Part D, we have 280 centimeters of mercury, and we're putting it into dynes per meter squared. Okay? So this is a similar kind of thing, except for there's a little bit of trick here where in the front of your book you don't have centimeters of mercury, right? So how do you change that into something that we do know? Well, we do know what inches of mercury are, and you can just treat these like you would treat any other length dimension. You would say there are 2.54 centimeters in 1 inch. That's what this conversion is, and now we've gone from centimeters of mercury into inches of mercury, and inches of mercury is in the front of your book. So inches of mercury into dynes per centimeter squared, but it asked for dynes per meter squared, so now we just change the centimeters into meters. Just make sure you're squaring those lengths and conversions, and that equals. Okay, so for this next one, it's starting to get a little trickier. It's saying that we start off in a vacuum, and we're going to gauge absolute pressure. Okay, so what that means is that we're starting off at a relatively negative pressure. It's negative compared to atmosphere. Okay, so what we do is we say, okay, how much atmosphere of mercury is there? There's 76 in 1 atmosphere, and we do 76 minus 20, so that is the actual pressure, not the vacuum pressure. It's the actual pressure inside of whatever this vessel is, and outside the vessel we've got an atmosphere, 1 atmosphere. Inside the vessel we've got slightly less than 1 atmosphere. We've got 20 less than 1 atmosphere, so that's what the pressure is in the whole vessel altogether. You do 76 minus 20, and then you just convert that into atmospheres. So there are 76 centimeters of mercury in 1 atmosphere. You finish the conversion. Hopefully you see how that works, where you've got a vessel. Inside the vessel, it's 20 less than what's outside the vessel. Okay? Okay, so now we're doing part F, and it's 25 psi G, 2 millimeters of mercury. Gauge. Okay, so both of these are gauge pressures, so they're referring to the same pressure. So we don't need to worry about compared to an atmosphere or something like that. These pressures are referring to the same vessel, so we can just keep it in the same units here, or we're changing units, but we can keep it to the same reference. So we've got 25 psig, and you just do the same simple conversion that we did before. Okay, now part G is the same question, except for now, instead of going from millimeters of mercury gauge referring to the same vessel, now we're changing our reference and we're saying we're not talking about what's inside the vessel, we're talking about total absolute pressure. So if you've got an excess of 25 psi inside of this vessel, what's the total increased pressure above that? So if it's 25 above atmosphere, then you say, okay, here's my psi in 1 atmosphere. I'm 25 above that, and I want to convert this whole thing into millimeters of mercury. So that's what you would do after you add the 25 above the atmospheric pressure. All right, so for part H, it's saying we have 325 millimeters of mercury in our atmosphere, but we need to turn that into gauge. Okay, so if we have 325 millimeters of mercury pressure inside of our vessel, we want to know how much above atmospheric pressure that is. Well, we just subtract out the atmospheric pressure. And it's actually less than 1 atmosphere, so we'll end up with a vacuum. So we actually have a vacuum pressure of 435 millimeters of mercury. All right, so for part I, this one was the most intense part of this problem. In part I, it says we have 35 psi, and I'm going to say that that's our pressure P naught. And we want to convert this pressure into a pressure head of tetrachloride, carbon tetrachloride. Okay, so one way to do this is to say, okay, so we have our pressure, and this pressure is being caused by a certain amount of head of carbon tetrachloride. Well, a head pressure is equal to the density of the fluid times the height of the fluid times gravity. So if you want to know the pressure head, you just solve for what the head is. And we do that here. We've got our pressure, we've got our density. So this is what we start off with. We convert it into pascals so that the units all work out. We're working in SI units. This is our acceleration due to gravity, or G. This is the density of carbon tetrachloride. And then we're converting into centimeters of carbon tetrachloride, not meters. So, and that's what that equals. Okay, the other method that you can do is say, okay, I know how many centimeters of mercury there are in an atmosphere, so I can just convert this into centimeters of mercury, and then if I know the density of mercury and I know the density of carbon tetrachloride, I can just take this ratio. So you multiply by the mercury. It's because densities are in the denominator. Okay, so you multiply by the mercury, and that cancels out the mercury head, and then you divide, like we did here. You divide by the carbon tetrachloride, and then you end up with the carbon tetrachloride here. And you can see that they're equal to each other, these two methods. So, all right, that is it for problem number 3.32. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem solving videos. Thanks again, and I'll see you in the next video.